two session chairs.
Hello, I'm Anna Horliston from the University of Bristol, and I'm your other session chair today.
And we have today the pleasure of introducing our moderator.
I'm Rezvan Sultanabati from University of Alabama.
Excellent. So we have a very interesting session this morning. We're going to be trying to combine petrology and geophysics, and the synergy between the two of them has not been achieved as much as it should be. So I'm hoping through the discussion, you all in the audience will be able to pull together some of that. So we've already now had one day's experience with this format. The format remains as you've already encountered yesterday, and that is this is a half session. We will have 6 back-to-back talks followed by a 25-minute question and answer session. We have 10 minutes per talk, and LPI has not graced us with even a second in between talks, which means that we have to push that 10-minute button even if you are still sitting in your chair and taking a sip of coffee. If we could get that light off, because that's right in our eyes. Thank you. So to allow you as much time as possible, we would like you to please walk over to the table before your talk, when the previous talk is still going, and get mic'd up, so that as soon as that person is ready to walk off, you are ready to walk on. And that's the only way you will get as close to 10 minutes as we can give you. So just be aware of that. But remember, if you walk back to your seat with the mic, you are not letting the next person get mic'd up. So think of it as a loop. You get mic'd up, you talk, you go back and drop your mic off. Thank you very much in that regard. Okay, so are there any other things? Yeah, so let me tell you about the timing. You will see from the podium, you will see on the floor is a timer, and it also has a light. You will have green light for 8 minutes, and then a yellow light for 2 minutes. And at 10 minutes, you will see the moderator, or not our moderator, but rather our session chair, the nice one over here, who's telling you, you got to wrap it up right now in 2 seconds because the next person's time is ticking. So anyway, please do be respectful to the person who's following you. Let's see if there's anything else I needed to add to that. Anything else you guys want to add? Yes, we have our session chair here who would like to say something about the poster session that goes along with this.
Yep. For anyone who hasn't read the schedule, we have a live poster session downstairs this evening from 6:30. So you can follow on the Martian geophysics and volcanism theme down there. I believe we're in the early 200s number wise. Well, at least I'm 201, so I assume everybody else is somewhere around me, hopefully. So yeah, please come to our posters later as well. The other thing we need to remind you about is if anyone would like to be a Dwarnik judge, they are still looking for more people to do that. So if you want to judge student posters and help them further their careers, then please search up on the LPSC website for how to do that. But it's a relatively simple process, but they would really like more people to judge things. So, and if you have signed up to judge one of our speakers today, please remember to do so.
Yes, absolutely. And you will see our wonderful session chair also there. So please do come and say hello to her. So I think that we are, can't think of anything more that you guys need to know. For those of you that are speakers, you have both a pointer and a slide advance there on the screen. The mic that is on the desk is not live. So what's live is what you're mic'd up with, and therefore you're free to turn around and wiggle if you're that kind of person when you talk. So what time do we have to start?
In less than 1 minute. So about time.
Okay.
We can introduce Simon.
Yeah. So the way this is going to happen to save time, we are going to introduce while the first slide is getting set up. So our first speaker today is Staller, who is going to be talking about Attacking a Martian Mystery, a review of swarm Marsquakes informed by deep learning. Thank you.
Thank you for the introduction. So I'm not Nikolai Dahmen, I'm Simon Stehler. Nico is a PhD student, and now postdoc who did a significant part of that work, and I'm just presenting it and giving a bit of interpretation. And as the title already suggests, it's really one of the last mysteries of the InSight data set where we don't even have a proper conceptual way of explaining what we're observing. And so what this talk is about is mainly to give that context to the larger audience. And hopefully somebody of you will come up with an idea of how to explain it and show you a few of the things we did over the last year to actually solidify the evidence that we're having here. So I'm starting with the basically the view of Martian seismicity as of yesteryear, and that is that, as we talked about quite a lot, most of the Mars quakes are happening in Cerberus fossae. So that's a very young graben system in Elysium Planitia, potentially related to a plume below the whole Elysium region. Another region where we had a ton of Mars quakes that was only discovered later in the mission is the Phlegros Montes, a last thrust fault, the largest thrust fault on the planet. Curiously enough, all these 6 events that we recorded there happened within 1 day, and some of them were the largest quakes that we ever observed on InSight. So that's not entirely unusual in terrestrial seismology, but it's just interesting to note. And then we were having this other type of quakes, the so-called swarm quakes or high-frequency quakes, and we want to term the phrase swarm quakes for those. There's a paper with my name on it in one of the big journals that says, oh, these swarm quakes all must be in Cerberus fossae as well. They are somewhere in the shallow part of Cerberus fossae. But then something happened last year, and really props to Valentin Bickel and the team, Kerry Wagstaff and some other people from JPL, who did a review of all CTX images from Mars Reconnaissance Orbiter looking for new craters. And they found a ton more craters than manual reviews had seen in the years before. And specifically, a second paper then led by Konstantinos Charalambos that identified one Mars quake with one very fresh crater. And what this led to is basically that crater is somewhere here in Cerberus fossae as well. And it required us, without going into the details now, to basically push these high frequency quakes out by a good factor of 80%. So they are now somewhere between 2,000 and 3,000 kilometers away from InSight, and we do not know where on this annulus they are. Oh. So that is the work that was done by Nico Dahmen, who is the first author here. And what he did, he developed a convolutional neural network to basically denoise the InSight data set and find more of these high frequency quakes. This here is a before and after view. That's day of the mission, time of day, between all the events that we had found in a manual review with the Mars Quake service beforehand, and then the quakes that were found using the convolutional neural network. And in total, that's a good, it's almost a factor of 2 more quakes that we're having. And the thing is, we can do quite a lot of statistics now with these quakes and really solidify a few things that we had seen before. And, oops, sorry, this is the extremely busy plot that Nico produced for me for this talk. And I'll go through that plot one by one to make it a bit more accessible to all of you. First thing is the distance of these quakes. So these quakes cluster around 2,500 kilometers away from InSight with a spread of roughly 600 kilometers. And this is a robust observation, so it's not that they could all be in one place exactly, and we would just have an uncertainty on how to determine the distance. No, actually, from the waveforms, they must have that certain spread. Now, the other thing, the median magnitude of these quakes is 1.8, which corresponds to a scalar moment of 10 to 11 Newton meters, which might not be helpful to anybody in the room who's not a seismologist. To give you an idea, that's a fault of roughly the floor area of this room that is rupturing during these quakes on the order of a few centimeters. So it's a small quake, but it's still a quite significant area that you need for that. If it were a landslide, it would be a landslide of a few million cubic meters of material, but we're pretty certain from the signal shapes that it's not a landslide. Basically, they are too fast for being landslides. Still, we think they are somewhere extremely shallow in the Martian crust. So the uppermost kilometer, maybe. Now, the second observation that we can do a lot more robust these days with the increased data set is basically the distribution of large quakes. Large quakes are here versus small quakes. So that's such a Gutenberg-Richter plot. And what we find is that we're having on the order of 1,000 magnitude 1.5 quakes for 1 magnitude 2.5 quake. And that is unusual because on Earth, you're normally having a factor of 10 between 1 magnitude and the next magnitude. So that would be the slope that we would expect on Earth, b equal 1 slope. That's the b equal 2 to maybe almost 3 slope that we're finding on Mars. And as I said, we're having by now enough quakes to actually call that a robust statistic. And now the last and weirdest thing about these quakes is actually their temporal distribution. So this here is, on the x-axis is L sub s, or the subsolar longitude, and it's basically once the first year of the mission, that is this line, and then the second year of the mission, Mars year 36, the second line. And what is plotted on the y-axis is the cumulative seismic moment for each year. So basically how much seismic energy was released by all quakes until then. And what you're seeing is that in the beginning, there are not a lot of quakes, but then you have a almost have a stable or linear slope. So you have a constant release of quakes, a few quakes a day, and then it tapers off before the northern summer ends. You see here the noise. So we could say in winter we had more noise. In winter, we don't exactly know whether we missed quakes. What we're pretty certain that in these transition periods, the noise was still low enough that we would have seen quakes if there had been one. So to summarize, what we're seeing is we're really seeing quakes only in northern summer, and we're seeing twice as much quakes in the second year of the mission than in the first one. And now, so basically these are the three observations, and really what I want to spend a bit time on in the rest of the talk, that just like the current political situation in this country, none of this is normal. That's not what you expect on Earth. So talking about the distance, that's one thing. I said roughly a distance spread of 1,000 kilometers. So it's certainly not Cerberus Fossae, that's too close. It's not Elysium Mons, somewhere where you would have relatively steep flanks on a volcano. That's also too close. It could be Isidis or Hesperia, Planum and Planitia. These are wrinkle ridges at the bottom of craters. Let's say the minimum distance matches the southern extent of stable subsurface ice, but only the minimum distance. It wouldn't explain why there aren't quakes at further distances. And then we're still having Flagros Montes, the large thrust fault in the middle, basically, of that distance range. If we talk a bit about the timing of those quakes, so that's an image from Bavaria with the Hochstaufen mountain. And the peculiar thing about this mountain is that whenever there's rain on this mountain, you do have quakes afterwards, in the days afterwards. So that's the thing we're observing on a few places on Earth, that also during snow melt or during rain, this is basically triggering quakes because you're releasing the normal stress on a fault and basically allowing the fault to rupture in this moment. Now, obviously, there's no rain on Mars. There's not even a hydrological cycle, so we don't. It's the only mechanism that we're seeing on Earth that basically water is allowing seasonal seismicity, but it's not a mechanism that would in any way be plausible on Mars. Nevertheless, I plotted here the temperature curve from the Mars Climate Database for northern 50-degree northern regions. And one thing you see that here, the distribution of our quakes, that really matches quite well with the times of the year when you're having the maximum diurnal temperature curve of a good 100 Kelvin. While in winter, when you're having almost no diurnal temperature change at 50-degree north, we're also not seeing any quakes. In the interannual variability of the quakes, so this is Mars year 35 and 36, these were the 2 years of the InSight mission. You basically don't see any distance in the dust storm, difference in the dust storm between those 2 years. Mars year 35 had a global dust storm relatively, 34 had a global dust storm relatively late. 35 and 36 did not. Yet, as I said, we're seeing twice as many quakes in Mars year 36 than in Mars year 35. And then the last thing, the distance, the size distribution. As I said, we're seeing a p-value of 2, maybe even up to 3 on Mars for these quakes. That's not somewhere we're seeing anywhere on Earth. We're sometimes seeing something like 1.5 or 1.6 between small and large quakes on Earth. Typically, that happens in volcanic settings where you're having very fractured fault networks. So that means that basically there's no, it's not possible to produce or to have a large fault under enough stress to really produce a magnitude 2 or 3 or 4 or 5 quake. Everything will basically rupture beforehand because the material is so weakened. Again, it's not entirely clear how this would be the case anywhere on Mars, but it's just the only kind of similar thing we're seeing on Earth. So to summarize, the neural network-based Mars-quake detection and denoising really confirmed these 3 observations that we're having. I would say the seasonality cannot explain somewhere in the near equatorial regions where you just don't have basically a large meteorological distance between summer and winter, a large enough one. It could be explained somewhere in the northern source region, But then even you would need local faults that are in enough stress to actually produce those quakes that are facilitated then by the seasonal cycle. But in the end, we don't have a mechanism yet, and I'd be very happy for any of the people who are looking at seasonal changes on Mars with imaging to tell me whether, hey, you have any idea what this could actually mean. And with that, I think I'm done. Thank you.
Joaquin Borealis impact as a source of crustal magnetic anomalies on Mars? Question mark. And this is given by Orlanducci.
So good morning, everyone. I'm Claudio. I'm a PhD student in Poland. So today I will show you my work, basically, which focuses on the magnetic anomalies on Mars. And oh, yes. So basically my works try to, as the main goal, to investigate the possible origin of these magnetic anomalies in the crust and try to understand how is possible this fossil magnetization which the planet has in the present time without an active dynamo. And basically what has been done is is a statistical analysis of the anomalies orientation and see if these their origins could be connected to one big event happened in the early history of the planet. And basically was being used the latest magnetic model field, which is by Langley 2019. And here we can see, you can see in the table the main parameters briefly. And we use for geological purpose the radial component because it's better to see before the planet, first the pattern of the anomalies, and then to see if there is some possible correlation with geological features. So, but this is the radial is best for this type of analysis. And so in literature, there is a big debate about the origin of the anomalies and about also the origin of some geological features. From one side, we have some early works which consider this putative origin to attribute to the Borealis impact basin in the pre-Noachian time and in the northern hemisphere. But there are also other authors which consider more endogenic processes as conventional model due to a possible impact in the southern hemisphere. So there is a big debate about this. And so we are trying to see mainly if this impact hypothesis could be tested and verified in some way, and if this Borealis basin is happening. So basically what is being done, the radial component is before filtered up to 100 nanotesla to avoid to have artifacts and possible noise in the data. And then has been used an algorithm, which is the skeletonization grid, which consists to identify the main pattern of the anomalies, in this case, the geometry, and then to give a segment, so called a magnetic segment, so we can see clearly which is the orientation and which is the shape of this anomaly, because sometimes it's not very clear. And then considering some fictitious centers, each 5 degrees on the whole surface, some geodesic computation to classify in circumferential and radial, which means that circumferential is the anomalies go around this impact center, putative, and radial go from the center toward the external. So we see of the data set is being so the anomalies are located, consider these fictitious centers and how much is their population occurs. And then on a random distribution, we define this threshold of 22.2%. So this means that taking so the anomalies for each type, the circumferential radius we consider are plus minus 20 degrees, as you can see in the shape here, shape here, and then consider the whole range we and divide it, which is 40 degrees and 80 degrees in total for both radial and circumferential together. And considering a random distribution of 360 degrees, we have this best threshold, which it's useful to understand the fixture center considered is statistically meaningful, so it could be a new possible location of a Borealis impact center or not. And then what we obtain is a density map, which is a representation of all the circumferential anomaly and radial anomaly classification compared to all the fixture centers on the planet on 5-degree grid. And we can see that in the northern hemisphere, there are new 10 centers, 10 fixture centers, which could be a new location, so we can improve the literature data about the location of the Borealis impact center compared to and among these, there is one which is located to 45-degree north, 155-degree west, which is the 42% of magnetic anomalies. So we are 20 degrees south compared to the literature data available, which is around, it's estimatory literature, but we are in this area. So this means that, that we need to understand now which is the possible basic geometry, what is being done. So starting from the world dataset, then we consider only the circumference anomaly related to these 10 fictitious centers. And the question is, if it's true that happened one giant event, and if could be an impact event, so which is the shape? Is elliptical impact or circular? So the question, so here we consider the distribution of these magnetic anomalies, try to set a possible geometry of the spacing, and from this result seems to be elliptical shape. And also this plot could explain that there is a good correlation with the anomalies, and most of them, so the 50% approximately, are connected to this one big event in the early history of Mars. And here in these maps, you can see in the first, there are the 3 models basically. So the first is from William Square in purple, which is center, which is the first interpretation of this Borealis shape using only topography, as we've seen before. And it's more circular, but then constraining, using as constraint and using an ellipse, which is center here, we perform this, and seems that in the Tarsis area there is a different shape, but approximately as our ellipse follow the dichotomy boundary, and it's clear how these anomalies are around this new shape that we obtain. So yes, and and then analyzing some geological pattern. For instance, this is the Nilo-Syrtis area. This pattern seems to be consistent with this direction, with this ellipse, and not with this other. Oh, but of course, in some point they are very similar, but this ancient feature, probably the geometry could improve the interpretation of the geological features too. But there are other areas which sometimes follow better these ellipses. So in conclusion, what this work do, it's of course is an improvement of previous literature data, because I think we constrain better some data where there is a lot of uncertainties and big debate. And the interpretation is that, yes, this magnetic anomaly distribution could reflect an ancient tectonic system with these fractures, which is typical of multi-ring basin, for instance. And probably this fracturing formed after this giant impact then has been fulfilled by some fluids, probably post-impact volcanic hydrothermal fluid, where the magnetite will crystallize. And probably later, new other events as volcanism could form other new magnetization. So also the dynamo probably could be extending over 300.7 in case, so this could be constrained better. But yes, I think that now the Borealis basin could consider these results could be considered something of concrete, probably really happened, and in the northern hemisphere, and probably something of hidden there is as these tectonic features, and I think are new information that will improve to understand how the magnetization, why the magnetization on Mars is present in the crust, and to start new way to see different. So thank you very much, and thank you for your attention.
Our next talk is crustal magnetization depth at Elysium Planitia, Mars, given by Sultanat Badi.
Hello, everyone. Today, I'm going to talk about crustal magnetization in Elysium Planitia, which our first speaker talked about. Here in the right, you can see the topography of Mars, which I have plotted, and also I have marked the region using a white circle over it. You can see the elevation in meter using the color. From studies after Mars quakes, we have this layering information for crust beneath the landing site. Up to first 10 kilometers, we have some volcanic and sedimentary material. After that, up to 20 kilometers, we have Utopia ejecta deposit. And after that, up to cross mantle boundary or 40 kilometers, we have some impact melt sheet differentiation. By this study, we want to know where or which of these layers carries the magnetization. Answering that question may help us to constrain the material in the crust or timing of the dynamo. Gang and Vizorek have found the magnetic source depths for this region between 8 to 52 kilometers. They have used the global model of Langley. But what we do here is different from previous study. Let's see what's the difference. The first step here is using the raw data, which I have plotted in the left, we create a regional model. So the first and main difference is creating a regional model, and using that regional model, I'm going to calculate the magnetic source depths for the region. Then the second step is constraining further that magnetic source depths we get from our regional model. For the second step, I'm going to use Mars crater database, and I'm looking at the raw data again, and I'm looking at the orbits that are passing through the crater, and I want to see if I can have any reduction or dip in the magnetic total magnetic field that we see over the crater. Here on the right, bottom right, you can see the total magnetic field over time, and this is just one example from the orbits that I have looked at them. Let's go into detail. This is the first step. I used nighttime low altitude MAVEN data, and I have used altitude cognizant Slepian function, and I created a regional representation of the magnetic field at the surface of the planet, which I'm showing in the right. In both plots, you can see the radial component, and I use the color to show this radial component in nanotesla. Left is the raw data, and right is the model that I have created. The next step is calculating a multi-taper local spectra using that regional model, which I have plotted using that black line here. And also I have shown the uncertainty using gray shaded area. Here I'm using Vizorek and Simon's method to calculate that multi-taper local spectra. The next step is fitting a theoretical spectrum to the observed multi-taper local spectra, which depends on a source depth parameter. Here, I'm using Vizorek spectrum, which mainly depends on two parameters. The first one is the spatial correlation length, which you can see in the top, and the second one is the source depth. As you can see, the shape and the strength of the spectra changes based on these two parameters. So what I'm doing here, I'm going to vary these two parameters and calculate a theoretical spectrum, which is this pink one here within this uncertainty range, and calculate the misfit between them. Here you can see the chi-square misfit between these two spectra, which I have calculated for different choices of the parameter. As you can see here, I have calculated chi-square misfit map, This is source depth, and this is horizontal correlation lengths. These gray shaded areas show the chi-square value. Darker means lower value for the misfit between these two spectra. Also, I have plotted the best fit, which is this white circle here, and is overfitting. A chi-square value of 1 means that our two spectra fits well within the uncertainty, which I have shown using these two solid line here. Also, I have plotted one standard deviation below and one standard deviation above that value, which is these 4 dashed line here. As you can see, based on our analysis, it's possible to have magnetization at any depths between surface up to the cross-mantle boundary or 40 kilometer. So what's the next step? I'm going to further constrain this depth range that I get from a spectral analysis. So I'm looking at Mars crater database of Robbins, because the minimum altitude of the data that I have used here over this region is about 122 kilometers. I'm going to look at the craters that have a diameter greater than 61 kilometers, or half of the minimum altitude, which I have plotted here in the left. I couldn't find any clear, consistent demagnetization signature within this crater. Maybe you ask why even I should look at the crater demagnetization. Because for Mars, we know that the craters with a diameter greater than 500 kilometers could have removed magnetized material up to a depth of about 10% of their diameter. So I was looking for something like a demagnetization signature that I can constrain my magnetization depths, which I couldn't find any signature of that. So let's interpret what I have seen from my analysis. This was from a spectral analysis. Then I look at the craters with a diameter between 60 to 166 in the region. That gives us a depth range between 6 to 70 kilometers, which I have shown using this faded white area here, which I couldn't find any signature of the demagnetization in satellite data that I have looked at them. So we interpret that the material within these steps are not dominating the magnetic signature we see at satellite altitude. Now let's compare how previous model and our model predict magnetic field at the surface of the planet, and compare that one to surface measurement. InSight measured a magnetic field for that location, which is relatively strong, about 2000 nanotesla, while previous model predicted a magnetic field which is much smaller, about between 200 to 300 nanotesla. And also I have calculated my model prediction. My model predicted a magnetic field which is, as you can see, higher than previous model, but it is still about 1/3 of the surface measurement. Why is the case? Why we see this big difference between model prediction and surface measurement? We think that there is substantial amount of magnetization within a depth that we cannot observe from satellite measurement, or it's too weak to be seen from satellite observation. So let's put our finding into the layering information that we had at the first place. This was from a spectral analysis, then we got this from a crater analysis, and after that, we got this from comparing model prediction with surface measurement. So we believe that the substantial amount of magnetization lies in Borealis impact melt sheet. We couldn't exclude there is a part in ejecta deposit, and also we found that, or we believe that there is most likely some magnetization at volcanic or sedimentary material within this top first layer. By leaving this comparison, I'm looking forward to your question. Thank you so much.
So our next talk is Constraining the Magmatic Evolution of the Elysium Volcanic Province, Mars. And this will be given by Ronnie.
Hey, good morning, everyone, and thanks for joining. Yeah. So today I will be talking about my ongoing work, that is decoding the history of magmatic evolution of Elysium volcanic province on Mars. And you might be wondering why I'm talking about the geochemistry and there is a background of InSight mission. So I will be integrating the geochemistry with the geophysical investigation to infer about the 1D model that we are going to develop for evolution of EVPL. So before going into the results, and I want to infer about why the Elysium volcanic province is so important to study, because if there is a lots of study which shows that there is a spatio-temporal evolution has been observed from northwest to southeast Elysium, and if you see that the age of northwest to southeast is also changing, which is like this is the older one and this is the younger one. And here you can see that the Cerebral fossa, which is one of the interesting topic in terms of the tectonically reactive region from the Mars quakes that we have from the InSight mission datasets. And recent publication from Scheller et al. And another Perrine et al. 2022 shows that there is a recent magmatic activity that is lying under this Cerebral fossa, which is lying at southeast part of the Elysium, which is like around 30 to 40 kilometers. And they said that it's like ongoing magmatic activities, which is resulting into this formation of the extensional features over there. So there is another so there is one hypothesis that is going on, that the magmatic activity we see today is the result of the melt migration from northwest to southeast, which is kind of a case of investigation that I am looking for. So, and the study is from the David Sesko 2017, and they said like the northwest, there was a recent melting zone lying at the lithospheric thickness of like few hundred kilometers, and northwest eruption happens, and after that there was a elastic lithospheric flux is taking over, and the melt was migrating to southeast of Elysium. So we want to test further for extension of this Cerebral fossa. That's why we are using the petrological modeling from the gamma ray spectroscopic datasets. We are taking the elemental data sets from the gamma ray spectroscopic data sets to infer about what are the melting or magma conditions where it was forming. And after that, we are developing 1D model from Berman using the thermoelastic state of properties. So these are the method that I was following. But when you talk about the GRS, and we know that the GRS is having a very large scale, so we are taking the average to infer about whether this is a primary composition or not. So we are taking potassium to thorium ratio. Sorry. Okay. So we are taking the potassium to thorium ratios, which shows that it is aligned well with the average Martian crust composition of meteorites and other average compositions. And we have a ternary diagram, which is for the low pH aqueous filtrations. And here you can see that our data sets of all these regions are lying within below this feldspar olivine line, and it is not altered. So from this, we can say that our study is broadly representing a not secondary, but it is a primary composition, which we can use for the petrological modeling. So we have developed the pressure temperature conditions at which our region has been formed. The magma is formed for Elysium, and it is like near to 2 GPa. And if you see that we convert it to the lithospheric thickness below 200 kilometers. So we are developing this model for Elysium. Using first with the bulk silicate mass composition from DW85 over here, and we also use the EH45, but here I'm showing the results of DW85, and The temperature profiles as an input is from the Palasa et al. To 2018. We have considered minimum, maximum, and mean temperatures. And here you can see that the results of density and the velocity is giving a very good combinations of phases from transition of olivine to wetzelite. And there is a thermoelastic boundary which is at 1500 kilometers. And to get more confident on our body, like 1D model, we have compared it with the recent studies from the MassQuakes and the InSight missions that is driven by the Khan et al. 2023 and Sumil et al. 2023. And here you can see that there is some change in the core compositions, because we have considered as a primary, it's a solid core. We have not considered the lighter elements yet. So which results into the positive mass composition, mass and the moment of inertia as compared to what we have actual from the Mars. So we can say that from this is ongoing work. So yeah, I'm these are preliminary results we are presenting over here. And for constraining the model further, I'm using the InSight mission investigation for MassQuakes for the Cerebral forces. But it's surprising. I am looking for the Scheller's new papers that they are talking about that all the MassQuake is not from the Cerebral forces. But for my study, I consider a few of them as an investigation. And one of them I'm presenting over here is 2035. And we have, these are the raw data, and we have the spectrogram over here, and try to find out the travel time for the different phases, P and PBS, and further on. And these are the travel times that we have find out from our seismograph investigations, which is showing that these events is well matching with the models, and this is somewhat deviating because this is the kind of noisy data that we have. And the model that we are using for finding the travel time is from Khan et al. 2021, which is considering, we are considering the 50-kilometer depth and giving travel time over here. And we are looking to find out the travel time from our 1D, which we have developed. So this is ongoing work. So I can summarize, and we are looking for few futures to include all the 1D model of lighter elements in the core modeling. So this is the kind of thing we want to do, and we want to include the Elysium volcanic province of GRS that we have developed in our model. So yeah, thank you so much for the. Okay.
We're actually 2 minutes ahead of time now, so which is quite improbable, but I think we should wait if everybody is happy, at least for another 90 seconds or so. So if you want to stand up and stretch your legs and then sit down again, but don't go far, please. Okay, we're going to get back on schedule now. So it's 9:05, and I have the pleasure of introducing my co-chair, Hannah Nick-Vasil, to give the next presentation for us.
So we've, at Stony Brook, have launched a very extensive experimental investigation to try to understand how magmatic degassing has affected the Martian surface, and particularly whether it can be, if that process can actually produce some of the extreme volatile enrichments we see in the Martian finds, and of course, modify the Martian surface waters that postdated them. But what we noticed very quickly is that unlike on Earth, where, let's go back here. Unlike on Earth, where we have a lot of water-rich magmas that lead to products, degassing products that are primarily hydrogen-bearing species like HCl, H2O, et cetera. When we are dealing with low OH systems, we find that we produce a lot of vapor-deposited material. This includes halides, and if it's a sulfur-rich system also, we produce a lot of sulfides, sulfates, and so forth, and these can readily contribute to the Martian finds. But of course, the question remains, are Martian magmas rich in Cl, sulfur, and low in OH? So what we're trying to figure out is there a way to determine that? Of course, when you're looking at fine-grained rocks, even on Earth, they primarily degassed. So we really are stuck trying to figure out, is there any information that we can get that would give us access to what were the actual volatile contents of Martian magmas? So one way of doing this, of course, is to look at terrestrial analogs. So when we look at the terrestrial systems in which we get igneous rocks, much of them simply do not apply. And what probably applies to the greatest extent is where we have rising asthenosphere, decompression, melting under thick crust. So if we look at that on Earth, we see that this is a temporal process whereby we start out with decompression melting, producing tholeiitic magma that can pond underneath the thickened crust. And as this process continues, this becomes thinner and thinner and eventually leads to rifting. Even though this is not exactly what we see on Mars, what we're able to do is to couple the experiments that showed us how magmas evolved at these different levels to be able to work backwards and look at Martian magmas. So in a sequence of this nature, we see very consistent chemical trends that are a function of the thickness of the lithosphere. And shown here is a total alkali versus silica plot for these trends. At deepest levels, we get these silica undersaturated rocks that end in phonolite. But as we get to shallower and shallower levels, we produce silica saturated rocks that end up with rhyolites of high sodium contents. And then eventually the potassic sequence is shown here in green. And finally, at the lowest pressure, we get these tholeiitic sequences that are dominated by olivine fractionation. So what we've done in the early 2000s from NSF-funded work is to get a better idea at the depths at which we form these particular suites. So you can see here that we've been able to match the evolution of these suites to a particular depth. And most importantly, we do not need any special mantle for this. All we need is ordinary tholeite to be able to produce these suite types. But in addition, what we were able to determine is what the water content was. Remember, ultimately, we're trying to look at things like chlorine-OH ratios in Martian magmas. So when we look at this, we have a framework of understanding chemistry in depth. So now the logical question is, where do Martian rocks lie in this context? So shown here in our next slide is a whole variety of Martian rocks. And again, there's a lot of uncertainties associated with these. And as you can see, they show a very strong clustering for this green trend, these potassic sequence. And before you leave with the idea that we know this so well, I just want to remind you that the actual uncertainties are quite strong on this. But nonetheless, I won't bore you with it, but when I take in all the uncertainties, we still see a statistical clustering on this green trend, which becomes really important because what do we know about this trend? Well, first of all, there are rocks on Earth that follow this trend quite readily, and they vary from, for example, the anorthosite sequences that have fine-grained rocks that are extremely iron titanium rich, we'll see that in a minute, all the way to potassic rocks that range from trachybasalts, trachyandesites, trachytes, and potassic rhyolites to the equivalent plutonic monzonites, monzocyanites, cyanites, and potassic granites. Really important is all this, you produce a lot of alkali feldspar. And those of you that have been following Martian petrology realize we see actually lots of evidence of alkali feldspar. So, but you'll notice for these green trends, we have two very different directions of evolution. One does not lead to potassic granites, other leads to these high potassium phthalitic granites. So let's try to get a better understanding of where Martian rocks might plot in this. Apologize, it's a very busy diagram and I will minimize it. But just to remind you what all of this is based on, this is based on experiments. Can we take, can we take a tholeite and have it, what happens as a function of depth and water content to the compositions of the evolved liquids? And as you can see right here, for example, at about 50 kilometers depth on Mars, this tholeite would lead to this very silica pore composition shown here by this trend, and shown here in black that this involves really high iron enrichment, titanium, phosphorus enrichment. In other words, rocks that look a lot like creep on the moon. And we find them associated with the northocytes on Earth in these regions where we have low water contents because of repeated upwelling of mantle. So I don't really think that we have many Martian rocks that follow that trend very well. But to make a long story short, if you look at what trend they seem most like, then you can see that you find here. So here are, again, the rocks that we were looking at before, the fine-grained rocks. And you could see they follow very, very nicely the trends that are laid by these higher silica rocks. So they move towards potassic rhyolites going through these trachyandesites and trachytes, et cetera, and monzonites, cyanites, and the plutonic version. And so because we can now match this with water contents, 0.4 weight percent is quite low for a tholeite, and we can match it to depths, we have a much better understanding of what kind of rocks on Earth we should compare these to try to look at the volatile budgets. So very importantly is this slide here. So let's go back one. So if we look right now at what we've concluded so far, that the surface rocks that are fine-grained seem to fit very nicely in this potassic silica saturated alkalic suite, where I mentioned before that we have these volcanic rocks. We see them in the Snake River Plain. We see them in craters of the moon, and that's the volcanic. And in these northocite sequences, these cyanide sequences, such as in Fennoscandia area, large areas of the Earth that we saw relatively dry tholeite ponding at mid-crustal levels. We also get these rock types that you've also heard bandied about among petrologists, starting at 2 minutes. Thank you. So these monzonites, monzocyanites, cyanites, and phthalite granites. The phthalite granite is an implication that we're looking at low water contents, rather getting amphibole and biotite. So what do we know about these trends? Well, experimentally, we know that we're dealing with fractionation at mid-crustal levels. Presumably, the density is not as great on Mars as it is for continental crust on Earth, so these tholeiitic magmas can ascend to shallower levels. We're dealing with low water contents. And what else do we know? These experimental pressures match very much what has been done by geobarometry on these rock types on Earth. So we're looking at crystallization at mid-crustal levels. We see accumulation, what the geophysicists have called a second moho in these shallow regions, particularly in, for example, the large regions of cyanite in Fennoscandia. And what we also say is that by studying these, we have better idea of what the volatile contents are of these kinds of rocks. And it turns out it's unique. It's extremely interesting. And so here I've just quoted Frost and Torre, 1989, because they were sort of the first to look at these and realize that these rock types contain extremely unusual volatiles. What they find is immiscible droplets of halide melt that are trapped in the growing igneous crystals, suggesting that these magmas were actually saturated with halides, and most commonly chloride. And what else do they have? They have CO2 bubbles suggesting there's going to be a lot of CO2 streaming, which we know can interact with pre-existing olivine to cause rims of carbonate. So what does it mean? If we take this along with experimental data on chloride solubility, that even as shallow as 0.2 GPa, remember we're about twice that, and magmatic temperatures, we can get up to 2.7 weight% chlorine dissolved in our magmas that would be required to be in equilibrium with chloride melts. So if we match our low water contents up here with our high chlorine contents, we're supporting high chlorine contents, we're supporting high Cl to OH ratios because of low water contents, and therefore we expect that a lot of this chloride will have degassed in these shallow rocks and contributed to the Martian finds. And the last thing I'm going to say in my 41 seconds remaining is, what's the story about sulfur? We talked about chlorine here. What about sulfur? Sulfur, a lot of these rocks are associated with massive sulfide deposits. There's plenty of sulfur that comes up, but remember, sulfur solubility is very low in silicate melts. And that has led to the sulfur paradox on Earth. How can you degas so much sulfur even on terrestrial volcanoes when the solubility is low? And it comes to the conclusion that what you have is admissible sulfide melts that also coexist with this, and these degas at the same time to give that strong sulfur signature to the Martian finds and transport with them a lot of cations. So I will end exactly there. 10 minutes is up.
Thank you. So our final speaker is online. So hopefully we have Peng Fang online. We will advance your slides. So if you just let us know when they need to be advanced, and we'll do that for you. Are you there?
Oh, yeah. Can you hear me?
Yes, we can. Thank you. I'll hand over to you now.
Hello, everyone. I'm Fang Peng. I will be discussing our radar study of the dielectric properties of subsurface lava in the Southeast volcanic province, Mars. The Southeast region is perhaps the most famous. Next slide. The Southeast region is perhaps the most famous volcanic field in our solar system. This is home to the largest shield volcanoes. The alignment of three shield volcanoes that makes up the Southeast mountains is clearly evident in this view. From north to south, these volcanoes are named Asclepius Mons, Pavnis Mons, and Arsia Mons. These three shield volcanoes are surrounded by close volcanic plain with relative flat topography across the western equatorial region on Mars. This flat plain area is the focus of our study. Geologically, most of the plain is covered by the AHV unit, with ages ranging from Hesperian to Armadonia area. Next, please. Various volcanic features related to lava flows are present in the TVP. This included long lava flows extending tens to hundreds of kilometers with clearly identified boundaries, volcanic winds that contribute to the plain-style effusive eruptions, and pit chains representing the collapse of subsurface lava tubes. Additionally, there are features indicating lava-ice interactions such as low-bed flows with levate channels, mesa-like low-bed features, and low-bed flows sourced from pit chains. All these features record a complex eruption history in the TVP, making the structure and composition of lava naturally complex and non-uniform. Next, please. Orbital subsurface imaging radar enables a large-scale detection and is critical for investigating shallow subsurface structure on Mars. Sherrod and Marsis are two well-known orbital radars that have been continuously exploring Mars for 20 years, accumulating vast amount of data. Previous studies using radar data in the TVP have revealed a dense basalt composition. Subsurface reflectors, which are interfaces between materials with different dielectric properties, are found in relatively confined areas covered by dust with low surface roughness. Next, please. The dielectric permittivity is associated with the density of lava and affects the speed of radar waves traveling within. The two-way travel time of radar waves in lava can be measured in the radargram shown here, but the thickness of lava can be directly or indirectly determined, such as by using topography data to measure lava flow thickness or by relating subsurface reflectors to surface exposures. The permittivity can be calculated using a specific equation shown here. Permittivity can also be inferred by assuming a topography of the substrate and performing depth correction on the reflector to find the best fit permittivity. However, in most cases, we still can't determine the thickness of the lava, especially for dipping reflectors. This leaves many reflectors unuseful, making it difficult to effectively constrain the physical properties of the subsurface. Next, please. And now I will introduce our method for deriving the permittivity of subsurface lava. We observed that multiple subsurface reflectors might appear in a radargram. For simplicity, we focus only on the shallowest layer, which represents the latest eruption phase. We use the wavelet-based method to accurately extract surface and subsurface reflectors, obtaining the two-way travel time of the lava and the echo power of all reflectors. We excluded subsurface reflectors and mimicked the side lobes of surface reflectors. The resulting reflectors shown here have a distribution clustered in mainly three regions: west of Ascalon moons, east of Pavonis moons, and east of Asen moons. Next, please. After obtaining the echo power and the two-way travel time, we fit a linear equation to determine the loss tangent of subsurface lava for the three regions. The resulting loss tangent for the three regions is promisedly about 0.01, which is the lower bound of typical basaltic lava estimated on Mars in previous studies. Next, please. Next, we estimated the permittivity, which is constrained in the intercept term of the linear equation that containing Fresnel equations. By constraint, we can directly obtain the distribution of parameters from an intercept term. This is because there are numerous viable solutions for the parameters in our radar model, which is a three-layer radar reflection model. Top layer is a thin dust mantle with a given permittivity of 2, representing loose dust regolith. The dust mantle thickness ranges from 0.1 to 5 meters, and the permittivity of the overlying and underlying lava ranges from 2 to 20, covering typical geological material from low-density volcanic ash or pumice to dense basaltic lava. Once we specify a thickness for the dust mantle and the permittivity of the overlying layer, we can calculate the theoretical permittivity of the underlying lava. Therefore, we establish a valid parameter space where the parameters conform to the Fresnel equation in the intercept term. Next, please. The valid parameter space are shown here. Given the overlying permittivity and the thickness of the dust mantle, we derived the theoretical solution for the underlying layer, which has two scenarios. Either the permittivity of the overlying layer is greater than that of the underlying layer, or it is smaller. Next, please. For each parameter combination in the valid parameter space, we use formula simulation to obtain the synthetic echo power distribution, which is roughly a Gaussian distribution consistent with the observed echo power distribution. However, since the synthetic distribution generally has a small variance for all parameter combinations, this is due to the non-uniform nature of the true parameters. We then compare the similarity between the synthetic echo power distribution and the true distribution and assign a density value to each parameter combination. Next, please. After performance comparison for all valid parameter combinations, we obtained the density distribution of each parameter. This density distribution represents the constitution of each parameter with higher values indicating a greater proportion. For each scenario, the distribution of parameters for the three regions is very similar. This is very interesting, and the thickness of the dust mantle centers at about 2.5 meters, while the permittivity of both the overlying and underlying layers exhibit a module value of about 5. Next, please. On Earth, a dense basalt typically has a permittivity in the range of 7 to 11. Our derived value of 4 to 5 for the dominant components of the lava is consistent with the moderate porosity in the basalt. We interpret this component to be the result of lava-water-ice interactions, which produce low permittivity porous lavas. Some basaltic rocks originating from lava ice interaction include scoria, pumice, and altered basalt. All these rocks have low measured permittivity and align with our measured permittivity of the dominant component. This image shown here is a vascular basalt rock in a tendrophyte. Next, please. Hello?
We have advanced it here.
Next.
Can you not see the conclusion slide?
Next, I can see the slide next to oh, okay, sorry. So to summarize the main conclusion, we found a uniform dielectric property across the surface volcanic plains. And the second, there are the dominant low permittivity component in the shallow subsurface lava. And finally, this low permittivity represents porous lava that indicates a history of lava-ice interaction. And finally, it's our reference here. Thank you for your attention.
Okay, thank you everyone for your fabulous talks. Now we move on to our panel Q&A. So if I could invite all our speakers back on stage. The observant of you will notice that I have now lost both my moderator and co-chair. So I'm going to attempt to moderate and chair and read questions. So if anyone is on Zoom and has a question, I will try to get to that. There are handheld mics up on the stage for the speakers here. And I hope someone will unmute our online speaker if needed. Let me try and find the Zoom. This would be good, wouldn't it? When you ask a question, please come up to the mics at the front and introduce yourself with your name and affiliation before your question. So I think if our speakers up there, are you all ready over there, panel? They seem to be having a chat amongst themselves. Okay.
Sorry, were you asking a question, Anna?
I was just checking you were all ready over there. Are you all ready? You're all in order now, are you? Okay, great. Well, in which case we'll go straight up to Mike here, the first mic.
Hi, Mike Story, Purdue University. My question is for Simon. Yeah, I like your talk. I don't really think this is the answer, but just in the spirit of thinking through all the possibilities, have you thought about the seasonal loading of the polar caps and potential associated displacement with that, and whether that could maybe activate some fault somewhere or anything like that?
We thought about it. I mean, one problem is that we're still a good 1,000 kilometers away from the southernmost extent of the polar caps, even in the winter. So there's not a clear correlation. And then, of course, you were mentioning that there could be some indirect force propagation, but honestly, I don't see how that would then lead to this relatively constrained distance range. It's not like we're seeing those quakes extending all the way up to 100-degree distance, which would be then beyond the pole, but we're only seeing them in this small range. And so that's...
Yeah, I think.
But then I'm not a modeler of lithospheric loading or anything. Yeah.
I think you can get displacement far away from the poles, but I agree with the second point about the concentration. So,
yeah, thanks.
Lon Hood, Arizona. This is a question for Dr. Orlanducci. Yeah, the second speaker.
Yeah.
I think what you were finding are magnetic anomalies that are concentric with the Borealis Basin, right?
Yes.
Which is kind of centered on the north North
Hemisphere.
Pole.
Yeah.
I'm a little worried that this could be an artifact of the model that you're analyzing. You're analyzing the Langley et al. 2019 model, which is a very good model, by the way, but it is a model, and you're fitting, or it's produced by fitting dipoles that are artificial dipoles below the surface that are on a grid, that are on a latitude, longitude grid. So I'm a little worried that there could be some artificial alignment around the North Pole.
Yeah, because one constraint is the filtering of the data. So can you, okay. The one constraint is the filtering of the data. So we try to, we try to improve this filtering, because we started, for instance, from 200 nanotesla to remove all the low intensities, because sometimes you have these big stripes which are really artifacts, really huge. But we are thinking that is maybe could be not enough. So we are testing various thresholds to see when there is the best to remove, or better, could be very difficult, but we are trying to see other threshold, and if there is a difference, and if some lineaments effectively could be as part of these artifacts. But this was I don't know if I answered the question.
Well, I just think that a better approach might be to start with the actual data, the actual measurements, and analyze that. Also, you could analyze a different model, like there's a Gao et al. Model that's out now that you could try analyzing that one too, to see if you get consistent results.
Okay,
So,
thank you very much.
Hello, my name is Kirsten Hottendorf, University of Iowa. My question is for our last in-person speaker, the speaker all the way to the right. I do not remember your name. I'm sorry. Hello. I wanted to ask you, especially with the knowing what you know now about, we have very good analogous rocks, well, as good as we're going to get for rocks on Mars. With the Mars Sample Return mission, there is an analog mission currently going on with trying to source rocks on Earth that we can use to learn more about our samples before we get them back. I do not believe any of the current samples are ones that you listed in your presentation, and specifically for rocks in like the Eastern Snake Plain. What would you think about, or would you encourage the analog team to start gathering samples from these places?
So first of all, absolutely. I think that's really vital, because the more we can learn about things that really do look like analogs, the better we are as far as interpreting context and other things. And all of those samples exist. There's been a lot of studies out there that work on the Snake River Plain, craters of the moon, which are the volcanic equivalents. And there's just a huge number sample base for the anorthosite and the cyanites and the monzonites. And don't forget, there also are these things called the AMCG suites, which are the anorthosite, charnockite, mangerite, granites. They're the same thing, but they're metamorphosed. And there's data on that too. So absolutely. And I think those samples could be readily obtained.
Yes, especially the Eastern Snake River Plain, where I guess just as a little to everyone, Eastern Snake River Plain, I've done research there. It's really easy and it's really cheap. You all should go and do research there. 100%.
Absolutely. I'll second that.
I'm just going to jump in. Sorry, Carrie. I've got a question online, which is also for Hannah. So I figure you've got the mic in your hand. So this is a question from J. Brian Balter from LPI. And it says, "Hi, Hannah. I noted that most of the plots you showed compared terrestrial rock suites to Martian surface rocks, and the experiments you showed were dry, but not CO2 or CL rich. Are there any experiments which assess the effect of high CL and or high CO2 contents on liquid lines of descent at the appropriate pressures and melt compositions for these rocks?"
So that's a very important question, because yes, indeed, these were NSF funded. They were very interested in the water and the pressures. And we have since done a number of CL bearing experiments, and certainly Justin Filiberto started this in my lab many years ago. To show that actually we're getting even more iron enrichment at the deeper level. But again, at shallower levels, it's not as much of an effect, except upon degassing. Then we get a huge effect on what the residual compositions are. So yes, we do have some. Primarily what we see is that relative, for example, olivine to pyroxene stability, you get more pyroxene and less olivine in these chloride-rich systems. And hopefully one day we'll be able to publish those results also. And what was the second? Oh, the CO2. So CO2 solubility, even for high CO2, really is very low. And therefore, it is not affecting, not like chlorine, which has a very high solubility in water. It's not affecting phase equilibrium. What it really does do is it readily exsolves, even at depth, and streams upward and can cause a variety of carbonation reactions. So experiments with CO2 saturation have really not resulted in any effect, even really of the solidus, because of the low amount of CO2. And even in these melt inclusions that they see, it's CO2 bubbles, it's gas. Thank you.
It's Kerry Nunn from JPL, and my question is for the second speaker. So you showed that the magnetization was like concentric rings around Borealis.
Yeah.
Do you think that the flow is outwards or around? Does that make sense?
So you mean the surface? Yes.
Yeah.
So usually there should be some features as we should go downwards from the southern hemisphere, so you have subvertical features to better constrain also the geometry, because in some areas it's very difficult because a lot of processes happen after. Yeah, typically we should have some subvertical feature from, as for instance, valleys, but it's not. We are seeing more the tectonic things because.
But may I
yeah.
just interrupt? Which way do you think the particles are aligned? That way, like away from the basin, or away?
In this way, yes,
Yeah.
yes. Basically, this should be the typical because they change the variation in toward the infrared of the basin. Yes.
Thank you.
Thank you.
Hi, Mark Panning, JPL. As a seismologist, I probably should be asking Simon something, but he asked all the questions that I would also have, and we don't have answers to them yet. So I'll ask about magnetism instead.
Yeah.
For the third speaker, Sultanabadi, I'm sorry if I said that wrong.
No, it's fine.
So it seemed like a lot of the constraints of your matching were coming from like the high degrees, 40 to 80. I was wondering how sensitive those higher degree terms are to how you did the regional model, how you created the regional model. Could that affect the results?
Our regional model is region specific. For a strong region, we have a regularization that is somehow stronger than when we are going to model for a weaker region. So it's not like that having a damping factor for everywhere. It's region specific. Yeah.
Adrian Brocker, DLR. I have two questions, if I may. Okay, first question is for the fourth speaker. As far as I'm aware, there is no clear continuity between volcanism at Elysium Mons and Elysium Planitia.
Mhm.
You have kind of a 2 billion years gap. So how do you explain this?
So you are talking about the chemistry or like the age?
No, yeah, just so you suggested that you might have a migration of melt from Elysium Mons to Elysium Planitia.
Mhm.
But if that was the case, you should see a continuity in volcanic activity all the way from 3.5 something to present day, which we don't really see.
Yeah, that's a good question because you know that Mars don't have a plate tectonic, so that is a kind of stagnant linked framework we have. And this is a kind of hypothesis we can propose, considering because there is a lots of eruptions that happen at the northwestern part of Elysium, at starting with the Hesperian age time period, and later on, because there is all the magma was accumulated near to the lithosphere, and it takes times to melt and migrate to the new directions. So that's why we are proposing that there is a melt migration instead of like we don't have like plate tectonics over there. So that's a kind of hypothesis.
But so Mars is cooling over time, so you would expect you wouldn't expect melt to migrate.
The same melt is not moving. It is having eruptions over the one part, and after that several times, if there is a continuous supply of the magma, it accumulates near to the lithosphere. And if it is not coming to this, because there is eruption is there is an increase of the load on the lithospheres. So there is a flexure, elastic lithosphere is there. So it will increase the magma force magma to go to the another directions, to new directions. So that's why we are saying like it's going to the southeast part, and we have a change in the age crater counting. We have a age counting from there. So that's why we are saying that one.
Okay, thank you.
Thank you.
Second question is for Simon. So if there is a plume underneath Elysium Planitia, the first initial phase is going to be uplift, and the second phase is going to be a radial spread of the plume beneath the lithosphere. And if I recall correctly, right where you see this high frequency Marsquake within the annulus should roughly correspond to where at least we expect the plume to radially spread. And yeah, I wonder if that could be an explanation.
So what you would be saying is that the quakes are really on that annulus. I mean, maybe just for context. So the reason why I drew the annulus is because we don't really know the distance. So we sorry, the direction. And of course now we're always taking the parsimonious answer. Oh, they're not actually on a circle that is nicely centered around inside, but they are in one place, and we just can't tell the difference. But what you'd be proposing is there's actually a mechanism that might explain that.
Yeah, not necessarily the annulus, but at least the radial distance of this quake roughly correspond to where we would expect the plume to spread laterally, and where the surface essentially would move.
I mean, interesting idea to look into, definitely. I mean, maybe two caveats here. Basically my points, or maybe my points 2 and 3 are, so one, the very strange Gutenberg-Richter relationship, which at least does not look like a typical tectonic quakes that are mainly caused through stress in the crust. And almost never for normal tectonic settings find something that is far away from a B value of 1 on Earth. And then, of course, the second thing, the seasonality. I mean, wouldn't really explain that, why we are seeing these quakes only in summer. I mean, of course, you might still have, due to the process that you're describing, the stress or the underlying stress, and then some additional modulating mechanism. And I'm waving my hands in the air because I don't know what it actually is.
Okay.
Thanks.
Thank you.
Kerry Nunn, JPL. So I have another question for Simon Stehler. So this is just to clarify, you think that they are swarms, that they are kind of, you know, that like they're quite localized, even if you, I mean, obviously you can't 100% tell, but do you think they would, that would be your likely interpretation?
So after taking the uncertainties and picking and so on into account, I think we could probably get to an extent of some 400-ish kilometers, which is then extended to the, what I said, 600, 700 kilometers just because of noise, basically. I think, I mean, typical what we call a swarm on Earth is, of course, not exactly that. Swarms on Earth are typically due to volcanic processes over a year or so, and not repeating things. I mean, as often in planetary science, we're taking a word from Earth and applying it to a geological process on another planet that looks somewhat similar.
That's what makes it fun.
Yeah.
So, and then just to follow up as well, the kind of two, you know, is it possible that we just happen to see this kind of strange snapshot in time, and, you know, like if we carried on looking, we wouldn't see these kind of repeating patterns?
Absolutely. I mean, that's the sad thing.
Sure.
I mean, that we saw only 2 years and we didn't see,
Yeah.
as I said, the 1 year with the big dust storm,
Yeah.
if it's atmospherically somehow modulated process. I mean, it would have been interesting to see it in that year. Would it be interesting to see what's happening now? But unfortunately, we just had this 2-year time series in a very much longer geological process.
Yeah, cool. Thank you.
I'm Xiao from Louisiana State University. I have a question for Dr. Rani. So what would you say could be possibly the heat source to have sustained the volcanism on Mars, especially in Elysium, from all the way back from 3 billion years old, you know, till the Amazonian? Do you have any intuition as to, could it be radiogenic heat source or tidal heat or whatever could have sustained the volcanism for so long?
That's a good question, but we don't know. So, but possible scenarios, I can say that is the radiogenic heat only that is interrupt when the planet was forming, and that could be a one source reason. But tidal is not one case that I support in that way. So I support that radioactive, there is a potassium thorium high things we have on the Martian surface. So that can be one reason that is supporting the heat production there. So yeah.
Well, the potassium and thorium enrichment is only present in the north hemisphere. Like there's like a lowland enrichment of potassium and
that is
and
present.
thorium.
That is present.
As present.
So,
Okay.
yeah.
Okay. Gotcha. Thank you.
Yeah.
Okay, do we have any more questions in the room? Because I think my schedule says we should be wrapping up with a session closure. So I'd like to thank you all for coming. I'd like to thank again our speakers. I think they all deserve another round of applause. So yeah, don't forget posters tonight from 6:30 downstairs. Come along and see all some more exciting science on this theme and many others, as I'm sure you're aware. Thank you all, everybody.